In these next two pages, we're going to give you a chance to practice the recognition skills that we've been trying to build up till now, just by asking you to match up yourself a function like this and the graph that it's associated with. So I'll give you a moment to think about that, look at the function, and then look at the shapes of the graphs and ask yourself which of these graphs matches z equals 2 minus x squared minus y squared. All right. Hope you pause before we jump into this if you still haven't got an answer. Let's rule out the easy ones. Definitely not that, and definitely not that. Why? Because this is nonlinear. We have x squareds, we have y squareds, and that means right away it's not a plane. So that shape is totally off our list. And so we can rule out C and E. That brings us back to these three shapes. There's a few things we can try right off the bat. My favorite is definitely using values for x and y, especially simple values like 0. At x equals 0, y equals 0, z is equal to 2. Oh, well at that point, this parabola, this parabolic bowl, looks like it's going through the origin, so that can't be right. The z value is nothing. The z value here is 0. And these ones, though, both could be at height 2. That's both certainly possible for each of these. All right, so we're down to two choices. One parabola opening downwards, one parabolic bowl opening upwards. I think you probably have some idea already given the sign changes here, but let's just reinforce how we would be sure about it. Let's look at what happens along x equals 0. Let's go in that direction. Again, this is circular, has circular symmetry is another way to rule out those planes. Circular symmetry. Along the x equals 0, so along the y-axis, what happens? We get z equals 2 minus y squared. And we can quickly sketch that out. We know that if we're drawing the yz plot, 2 minus y squared is a parabola that starts at 2 and opens downwards. And so the only possible choice that fits all those criteria, circular symmetry, nonlinear, going through a positive x coordinate at the origin, or positive z coordinate rather, at the origin of x and y, is going to be B. And it can't be D then. So hopefully that agreed with your own logic. Let's take a look at another example. Much more exotic family of functions here. So z equals 1 over x squared plus y squared. Let's take a look at that and take a look at your graphs. All right. I hope again you latched on to the circular symmetry. It's going to be a common theme in when we recognizing or generating graphs, just because it makes the problem solvable. And as soon as we recognize that circular symmetry, we can rule out 3 of the different shapes we have here. This isn't circular, it doesn't have the same shape in a circle around the z-axis, neither does this, neither does that. It's worth talking about that one in a second just to see what it might have been. But for this initial question, those 3 are off the table. Now we're left with deciding between these two, which are circularly symmetric. There's a few ways you can approach this. One is what we just did before. I'll show you both the techniques and then let you decide what the final answer is. If we let x equal 0, then the profile we get is 1 over y squared. And you know what that looks like in terms of a YZ graph. It looks like this, 1 over y squared. Another way to look at it is the signs. Sine of z, well, it's the sine of the right-hand side, so that's going to be positive because 1 over x squared plus y squared is certainly going to be positive everywhere. Well, that rules out E here. So it can't be E, it will be A. trying to think of any other features that would distinguish it. It's a bit tough to say. You can certainly say there's an asymptote or something here, but that really comes most clearly through the letting x equals 0 part and seeing, oh, I know the shape of that 1 over y squared function that's going to be spun around the axis. There's other cases you'll see in your assignments where having a discontinuity at the origin may or may not be visible depending on limit stuff. Just as an aside, it's worth talking about what these other ones might be. This one is a ribbon shape. Notice it's the same shape no matter where we are in x. So what this might be is something like z equals negative y squared. When we go out in y, we see a downwards parabola, and when we change x, nothing happens. X does not affect our heights, so that might be a function or a formula for this one here. This family, or this graph here, we saw something similar. It has a circular symmetry. And what might it have as a function? Well, we actually saw something that would do that shape, that would produce that shape, except this graph is always positive. So what might we do? We might add a negative sign out front, and that would flip it in the z direction. So it becomes, instead of the bell-shaped hill, it becomes a bell-shaped valley. And that occurs because every positive z value that we had before would be inverted, would be flipped of sign, and it would end up below the xy plane on the negative side, and so we'd have a bowl shape instead of a hill shape. The other functions are a little more cryptic. We need some axes. This is probably something like a cubic, but it's hard to say. It's enough for now to recognize, okay, there's some basic forms that we might at least have a guess as to what the formula is, and if we're given a formula, we should be able to at least eliminate graphs that do not match what we're looking at in terms of the formula.